Okay, we are interested in finding a formula for the scattering cross section. To get this, we constructed we will construct wave packets. Let us say you consider the particle 1, it will be localized in the position space at some point, and also it will be localized in the momentum space. There is going to be a distribution, I will call this 2 pi cube to k0 f1 of k, and then so this function f1 of k determines the distribution in the momentum space. For particles which are eigenstates of the momentum, this f1 is delta k minus k1 bar. So, f1 of k will have some distribution in the momentum space, and then I will assume that this has a spread in the momentum along some value which I will call as k bar. If I consider two particles, then the wave packet for the two particle system, which I will call as particle 1 and particle 2, will be given by dq k1 over 2 pi cube to k1 0 f1 k1, then dq k2 over 2 pi cube to k2 0 f2 k2 k1 k2. We would like to find the transition probability of this state evolving to some final state f as t goes to infinity. So, what we need is the transition probability for this process, which is given by the mode square of this quantity. I will call this as W for some initial state I going to a final state f. So, this transition probability we can work it out. Let us do it in step by step. This is basically d cube k1 over 2 pi cube to k1 0 d cube k2 over 2 pi cube to k2 0. Then there will be complex conjugate of this quantity, which will give me d cube k1 tilde over 2 pi cube to k1 tilde 0 d cube k2 tilde over 2 pi cube to k2 tilde 0. Then I will have four such quantities. They are f1 k1, f2 k2, and then I will put a star here because of the mode square, f1 k1 tilde, f2 k2 tilde. Then the inner product of f with this quantity f k1 k2 star and f k1 k2 k1 tilde k2 tilde star. However, thank you. That is one point. The second point is that this the in space is not same as the out space. So, the transition probability will also involve the S matrix. Therefore, I will have what I am actually interested to compute is either everything I can work in the in Hilbert space or I can work everything in the out Hilbert space. So, therefore, the probability amplitude actually involves a factor of S here. Okay. So, strictly speaking, so actually what I will have is f s k1 k2 star times f s k1 k2 tilde, where in this expression I am assuming that everything the state f, the states k1 k2 all are state vectors of the in Hilbert space, the in space. Actually, we do not even need this, because this S matrix contains an identity piece, and then the remaining terms I am denoting that by I times some operator t. The first term gives the forward scattering part. So, even in presence of interactions, if I consider a beam incident on a target, there is a finite probability that the particles will just pass through each other without interacting, and that is what is the forward scattering part, that is given by this identity term here. So, I am not interested in the forward scattering part of the cross section. So, I will forget about the one term here. So, therefore, I have to write I times t here similarly I t. Okay. So, this is what we want to compute. To do this, let us introduce this identity. So, we will do one more thing. This matrix element here, both these matrix elements, they describe the transition probability. If I forget about the forward scattering part, they describe the transition probability from some state k1 tilde k2 tilde to some final state f. This transition will conserve energy momentum. Therefore, the matrix elements here f I t k1 tilde k2 tilde, this will contain a delta. We do not know the exact form of this matrix element here, but we know for sure that whatever it is, it will contain a delta function which will conserve the energy momentum in this process. So, this just basically gives k f minus k1 tilde minus k2 tilde, a 4-dimensional delta function. For convenience, I will put a factor 2 pi to the power 4 here, and then the remaining part of this matrix element I will denote it as f I some script t k1 tilde k2 tilde. So, this is basically the definition of this matrix element here. Depending on the exact form of the interaction, I will have exact expression, at least an infinite series expression for this operator I t, and correspondingly I will have an expression for the matrix elements here in the right hand side. So, I can substitute it in this expression, and when I substitute that, what I will get for the transition probability is W for some initial state I going to final state F, which is mod square. This quantity is nothing but dq k1 tilde over 2 pi cube to k1 tilde 0 d cube k2 tilde over 2 pi cube to k2 tilde 0, then f1 k1 star f2 k2 star, and then f1 k1 tilde f2 k2 tilde. Then I will have 2 pi to the power 4th delta of k1 plus k2 minus k1 tilde minus k2 tilde, and then 2 pi to the power 4 delta k f minus k1 tilde minus k2 tilde, where in the first delta function, instead of kf, I have instead of kf here I have put k1 tilde minus k2 tilde. That is because it is already multiplied by another delta function. This times the matrix elements here f I t k1 k2 star and f now I will make the assumption that the distribution is peaked around certain value k bar. So, f1 k1 has a peak around k1 bar, and same about f2 k2, it has a spread in the momentum, but the spread the distribution has a peak around certain mean value, and I will assume that the amplitudes here are actually close to some quantity which is f I tau k1 k2. They are non-zero only when they are significantly different from 0 only when the momenta k1 and k2 are equal to k1 bar and to k2 bar, and same about these quantities here. So, with this assumption, what I will do is that in both these expressions I can write instead of k1 k2 here, and instead of k1 tilde k2 tilde I can write here k1 bar k2 bar and so on. And the second thing is I can write this, I can consider this representation for this delta function, which is delta k1 plus k2 minus k1 tilde minus k2 tilde is equal to 1 over 2 pi to the power 4 integration d4x e to the power I x dot k1 plus k2 minus k1 tilde minus k2 tilde. I will substitute it here, and in addition I will use this expression for Fourier transform f tilde f1 tilde of x. I will denote this to be the Fourier transform of f1 k1. So, this is integration d cube k1 over 2 pi cube to k1 0 f1 of k1, and similarly there will be Fourier transform of f2. When I use that and when I use this expression for the delta function here, you notice that this term here will give me one f1 tilde star, this will give me an f2 tilde star of x, this will give me f1 of x, this will give me f2 of x, and there will be an integration over x. The k integrations will go away because of this definition of the Fourier transform here, and because of the fact that the only k dependence comes through these functions f1 and f2. I am ignoring the k dependences in all other terms. I am substituting instead of k1 k2 k1 tilde k2 tilde, I am substituting the average value of the momentum, which is k1 bar and k2 bar. Therefore, the only k dependence comes through this, and hence I can simply substitute the Fourier transforms here. When I do that, what I get for the transition probability is that W d4x times mod f1 tilde x square times mod f2 tilde x square, and then 2 pi to the power 4 delta of kf minus k1 bar minus k2 bar, and then f I tau k1 bar k2 bar mod square. This is what is the total transition probability, and hence the transition probability per unit volume per unit time, which I will denote as dW over dV dt, is basically the integrand without this factor d4x. So, this is f1 tilde of x mod square, f2 tilde x mod square, then 2 pi to to the power 4 delta kf minus k1 bar minus k2 bar, and this quantity here modulus of f I tau k1 bar k2 bar mod square. To get the cross section, I have to divide this quantity by the number density of the target, which I am considering particle 2 to be the target and particle 1 is the incident beam. So, let us consider the laboratory frame where particles of type 2 are in rest and the incident beam consists of particles of type 1. So, there are two things that we need to determine. One is the number density of particles of type 2, number density of the target, and the second thing is the flux of the incident beam. So, both these quantities we can determine from these quantities f1 tilde and f2 tilde. Remember, this f1 tilde of x satisfies the Klein-Gordon equation for particles of type 1. This contains the positive frequency part. I am sorry, there is a e to the power minus I x dot k1, because I am considering the Fourier transform here, there is an exponential factor also, and this quantity f1 tilde of x is the Fourier transform of f1 of k1. As you can see, this f1 of x captures only the positive frequency part, and this satisfies, this is a complex scalar field. You can show that this satisfies the Klein-Gordon equation for particles of type 1. Similarly, when you consider f2 tilde of x, which is dq k2 over 2 pi cube 2 k2 0 f2 of k2 e to the power minus I x dot k2. This will represent the positive frequency part of particles of type 2, and this will satisfy the Klein-Gordon equation for particles of type 2. We can consider the conserved current for these fields f1 and f2. For the field f1 tilde of x, let us call the conserved current to be J1 mu, current density, which is basically I times phi f1 tilde star of x del mu f1 tilde of x minus del mu f1 tilde star of x times f1 tilde of x. This is the current density for particles of type 1. Similarly, you have current density for particles of type 2. which I will call as J2 mu of x. This will have an identical expression with F1 replaced by F2. I F2 tilde star del mu F2 tilde minus del mu F2 tilde times F2 tilde. This is the current density for particles of type 2. What will be the number density? While quantizing the free field, we have already seen that the J0, the 0th component of the current density, gives basically the number density here. So the number density is just given by, let us say if I consider particles of type 2, then the number density of particles of type 2 is given by dN2 over dV. If I denote the number density of particles of type 2 to be dN2 over dt, this is just given by J0 2 of x, which is nothing but I times F2 star of x, F2 tilde star of x, del 0 F2 tilde of x minus del 0 F2 tilde star times F2 tilde of x. Okay. Now, look at the expression for F2 tilde of x. This is basically the Fourier transform of F2 d cube k over 2 pi cube 2 k 0 F2 of k e to the power minus I k dot x. But this F2 has it has a distribution which has a peak at k2 bar. Therefore, the F2 tilde here will roughly be F2 tilde of x will be given by some e to the power minus I k2 bar dot x times some F2 of x, where F2 of x will be some slowly varying function of x. That is because of this distribution here, it has a peak at the value k2 of x. If it was a delta function, then you would simply get e to the power minus I k2 dot x, but there is a finite distribution in the momentum here. So therefore, it will have a part which is e to the power minus I k2 dot x times some function f2 which is slowly varying. So when I put this expression here, what I get is this will give me twice k20 times mod f2 tilde of x square, right. So therefore, the number density of particles of type 2 is basically given by this. What about particles of type 1? What will be the flux of these objects? The flux is going to be basically the velocity of the particles velocity of the beam times the number density of particles of type 1. So, what is the velocity of particles of type 1? The velocity will simply be given by, so let us summarize this. For K20 bar, thank you. This is the same as this f because of the phase vector here, but here I will have a K20 bar. So, for particles of type 2, dN2 over dV is given by 2 K20 bar mod F2 tilde of x square. Similarly, for type 1 particles, again the number density, the expression for the number density will be similar. So, for type 1 particles, dN1 over dV, I can call this, it will have the expression which is 2 K1 0 bar times mod F1 tilde of x square. However, the velocity of particles of type 1 will be given by the momentum P1 K1 bar divided by m1, where m1 is the mass of particles of type 1. Okay. So, this will give me the flux of the incident beam to be twice K10 divided by m1 times K1 bar times mod F1 tilde of x square. You can either compute it this way, or you can directly compute this expression from the ith component of the current density J1 I of x. You can consider that, and then you can evaluate this expression directly from there. Now that we have all these things, we can compute this scattering cross section, and so the cross section d sigma will basically be the transition probability per unit volume per unit time divided by the number density of target times the incident flux the magnitude of the incident flux, which is basically these quantities here, f1 tilde of x mod square f2 tilde of x mod square times 2 pi to the power 4th delta kf minus k1 bar minus k2 bar times mod f I t k1 bar k2 bar mod square, this quantity divided by the number density there is twice k20 bar mod f2 tilde of x square times twice k10 over m1 mod k1 bar mod f1 tilde of x square. Okay. So, as you can see, this will cancel with this will also go away. What will remain here is this is 4 k10 k20 bar k10 bar and mod k1. Okay. So therefore, so the cross section is given by d sigma equal to 2 pi to the power 4th delta of kf minus k1 bar minus k2 bar times mod f I t k1 bar k2 bar mod square divided by four into k1 bar 0 k2 0 bar divided by m mod k1. Okay. So, actually for the particle of type 1, the flux which is given by the velocity times number density which is dn1 over dv, and what we have is the velocity is mod k1 divided by m, the number density is k10 bar mod f1 tilde of x mod square. Actually the velocity is not k1 bar divided by m, but it is actually k1 bar divided by k10 bar. This is because for a relativistic particle, you know, the momentum k1 bar is just mass m1 divided by square root of 1 minus v1 bar square times v1, and we have to solve this equation for the velocity. So, this simply implies k1 square, k1 bar square is m1 square v1 square divided by 1 minus v1 bar square, or in other words k1 bar square minus k1 bar square v1 bar square equal to m1 square v1 bar square. If I take it this side, then what I get is k1, this is mod k1 bar square. So, this is mod k1 bar square. So, mod k1 bar square is equal to v1 square times mod k1 bar square plus m1 square, which is nothing but k10 bar square. Therefore, the velocity is simply mod k1 bar divided by k10. So, here therefore, the velocity is not k1 bar divided by m, but it is k1 bar divided by k10 bar. So, I have the flux for particles of type 1 is simply k1 bar modulus times mod f1 tilde x square. Therefore, the cross section here is instead of dividing by m here, what I will have is I will have k1 bar 0. So, k1 bar 0 it will cancel with this. Therefore, the cross section is given by 4 k20 bar k1 modulus, k1 bar modulus, and I would like to write it in a Lorentz invariant fashion. So, the denominator, in the numerator everything is fine, but in the denominator you note that 4 k20 bar k1 bar is nothing but 4 times k20. K20 bar is nothing but m2, because we are working in the rest frame of particles of type 2. This is simply m2, and this one is k10 bar square minus m1 square to the power half. If I take this m2 inside, then I have 4 m2 square k10 bar square minus m1 square m2 square. Again, because we are working in the rest frame of particle of type 2, so this is simply equal to k1 bar dot k2 bar square. Therefore, the denominator I can rewrite it as 4 k1 bar dot k2 bar square minus m1 square m2 square to the power half. Therefore, the cross section is now given by 4 k1 bar dot k2 bar square minus m1 square m2 square whole to the power half. Now, we have the cross section where this quantity is actually Lorentz invariant. All right.